we will see three-phase circuits because these are useful to understand AC generator or motor. Okay, and yeah, star to delta and delta to star. Second thing we will see star to delta and delta to star. So there will be three-phase configuration. Okay, I already told you about delta to star and star to delta conversion because the basic difference between single phase and three phase is in single phase there will be only one coil in single phase circuit, single phase, but in three phase circuit there will be three coils or conductors, you can say R phase, Y phase and B phase. So three coils will be there, and that's why there will be three currents, three voltages and three phase power. This will be related to three phase circuits. So these three coils can be connected either in star or in delta connection. What is star? Star connection will be like this and delta connection will be like this. So three coils will be connected in star like this. Okay, R, Y, B, or in delta R point, Y point and B point. Okay, like this. So first of all, let us see how to convert the given network from delta to star. So this is given in delta. We have to make it as star connected network. Then first of all, you have to take three resistances as three resistive elements are given. Instead of resistance, they can give impedance also, R plus minus J X form. So you have to perform the same operation. Okay. So this is the resistance. Let us say this is RA and this is RC and this is RB. So how to calculate RA? RA is involved between RAB and RAC. Okay, so you in the numerator you multiply these two resistances, and in denominator in all the cases this will be same. Means RAB plus RAC plus RBC. So that is the trick to remember the formula. Now how to calculate RC? This RC, as you can see, RC is related to RBC and RAC. Okay, so in numerator you just multiply these two resistances, or denominator for all the resistance values will be same. So that is the trick from delta to star conversion. Okay, now from star to delta conversion, how to calculate the resistance values? You please make the circuit like this first. This will give you RBC because this is connected between node B and C. This resistance is connected between A and B, and this resistance is connected between A and C. Okay, yeah. Then how to calculate RAB? Let's see. The numerator values are same in all the three cases. Okay, so this will be common. You just multiply RARB plus RARC plus RBRC, means multiply two resistance values. Okay, means RARB RC, this and this. Okay, so numerator value will be same, and the denominator, what is the difference is, as it is RAB, means the resistance is connected between A and B. So you please take the different means resistance, that is RC in the denominator. Likewise, in case of RBC, you please take RA, and in case of RAC, you please take RB. So this is the trick to remember the formula. Okay, and this is the example. So you will be able to solve this example easily. I am leaving this for you. Then now we will see the difference between single phase circuit and three phase circuit. Okay, this first of all, what is a single phase circuit? Till now we have seen single phase circuits. For example, this is a voltage source R, L, C. Okay, this is a single phase circuit. Likewise, this is also a single phase circuit. Why? Because the voltage source is like this. There is only one phase. means this is at a higher potential, this node, and this node is at lower potential, means it is grounded. So there is only uh, one voltage source, okay, and there is no phase difference between these two sources. Also, means phase difference can be there, but the potential difference between these two is Vt only, okay. Yeah, so this is a single phase, means this conductor is the written conductor, and this conductor is the live conductor. Live conductor means it is at the positive potential, and this conductor is at the negative potential or grounded. So there is only one phase. This is the phase, and RMS value will be its phase value, okay, and Vm is the maximum value, right? So what is the single phase power? So you already know that the single phase power will be Vrms, Irms, and cos phi. Phi is the angle, phase angle between Vrms or V and I. Okay, so this is how you can calculate the single phase power. Yeah. So in case of single phase circuit, there will be two conductors only. One is the phase wire or live wire, and the other is neutral wire or grounded wire. That is the single phase circuit, okay. Then V is the voltage of the single phase, that is the phase voltage. I RMS is the phase current, and cos phi is the power factor of the single phase circuit. Some key aspects of single phase power includes it is suitable for the small residential loads and small commercial establishments, but if you want to go for the industries, then they have to take three phase power only, okay, in order to drive large loads. Then the second thing is that the current and voltage vary between positive and negative peaks with a time gap of 180-degree between them. And the third thing is large inductive or capacitive loads cannot be directly connected because they need three phase power, because the loads means loads are large, okay, means load value is large, means they can take some kilowatt of power, okay. That's why we prefer three phase power in order to drive large number of loads. Now we will see three phase circuits in our households or in industries. They need three phase power, okay, or AC motor or generators can be driven by both single phase circuit or three phase circuits, but this three phase circuit is three phase source is preferred over single phase source. We will see the limitations of single phase source. So the three-phase power is mainly used for the generation, transmission, and distribution, because we want to generate bulk amount of power in order to transmit the and distribute to different households or industrial loads, okay, of electric power because of its superiority. Three-phase circuits have superiority over single-phase circuit. So power in three-phase circuits. Three-phase power involves the supply of electric power using three conductors. As you can see, there are three different circuits, okay, and these three circuits can be configured into these two connections. Either you can connect these coils or circuits in star connection or in delta connection according to your applications, okay. So these three sources will have 120 degree of phase displacement. Let us say E1 will be at 0 degree, then E2 will be at minus 120 degree, means after 120 degrees, and E3 will be at minus 120 minus 120, means E3 will be at minus 240 degrees. So the 240 degree of lag will be there with respect to E1, and that is called the phase displacement between the among the three voltages E1, E2, E3. E1, E2, E3 are the voltage induced voltage in three coils. These are the three coils, okay. These are the three coils. E1, E2, and E3 will be induced induced EMFs or voltages, and these three coils will have I1, I2, and I3. Okay, so even if even is at 0 degrees, then after 120 degree E2 will be there. Then after 120 degree, yeah, if you are rotating in this, if it is rotating in this direction in anti-clockwise direction with omega radian per second, then first of all even will come. After that E2 will come, and after that E3 will come. So that is the convention. So 120 degree phase displacement will be there. 120 degrees. That is the phasor representation of E1, E2, and E3, and these three are induced voltages in three coils of a three-phase circuit. So there are some basic points regarding your three-phase circuits. You can study from these topics. Okay. Yeah. One more thing I wanted to tell you that let us say this is R phase, this is Y phase, and this is P phase. We have to give names like this: R or A, B or C. So there will be the phase sequence. Okay. Phase sequence will be R, Y, B. This is called as positive phase sequence, and RBY will be negative phase sequence. We will see it later. They have mentioned RYB as positive phase sequence and RBY as negative phase sequence. Then how to write the equations of E1, E2 and E3? Even will be, you can take either cos or sine. Both are applicable. Okay. 2t cos omega t means this will be even RMS value at an angle of 0 degree. Then E2 will be uh, E2 RMS value at an angle of 2 pi by 3 means 120 degrees. Okay. So that will be at minus 120, and E3 will be what? E3 RMS value. Capital E3 is the RMS value of E3 voltage at an angle of minus 240 degrees. Okay. Small E2, E3 are the instantaneous values of the induced EMFs that are induced in the three coils of R, Y, B. Okay, R is the phase, Y is the phase, and B is the phases, and these three are three phases of a three-phase circuit. Understood? This is E1, this is E2, and this is E3, and in these three coils I1, I2, and I3 will flow. One more thing is there, the summation of E1, E2 and E3 means their instantaneous value. Some of their instantaneous values will be 0. You please remember this. Always this will happen in case of a balanced system. Means in a balanced or symmetrical system. What is the balanced system? Is the phase displacement will be 120 degrees only, and the phase sequence will be R, Y and P only. Okay. Yeah, a three-phase system is symmetrical if and only if these are the conditions. First of all, a load of each phase. Let us say these three are the phases. So we have to connect one load, the second load, and the third load in R, Y, or B phases. Okay, even E2 and E3. Load 1, load 2, and load 3. And you will see means these three coils can be connected either in star or in delta. So these three are the loads. Okay. So what is the condition? A load of each phase has equal impedance value. Means Z1 should be Z1, Z2, and Z3. So Z1 equals to Z2 equals to Z3. This is the first condition. Second, a load impedance of each phase has equal phase angle. If Z1 has theta 1, then and Z2 has theta 2 angle, and Z3 has theta 3 angle. So the angles should be equal. Theta 1, theta 2, and theta 3 will be equal. So that is the second condition. The third condition is that voltage and current values are equal for each phases. Means I1 RMS equals to I2 RMS equals equals to I3 RMS should be equal. Likewise, V1 RMS equals to V2 RMS equals to V3 RMS. This is the third condition. I1 is related to R phase, this is related to Y phase, and this is related to P phase. Okay, this is the third condition, and the fourth condition is that 120-degree phase displacement will be there between V1, V2, between V2, V3, and yeah, yeah, between V2 and V3. If V1 is at 0 degrees, then V2 will be at 120 degrees, and V3 will be at 240 degrees with respect to V1. Okay, this 120-degree phase displacement will be there between any two voltages. So these are the conditions for a balanced or symmetrical system. Now this is the waveform. Let us say, yeah, we want to represent our three-phase sources VR, Vy, and Vp in this diagram. So yeah, if it is VR, means VR at an angle of 0. So this is VR. Then Vy, yellow. Vy at an angle of -120 means Y phase voltage is lagging behind VR voltage by an angle of -120. Okay. If it is 0, this is 90, this is 270, this is 180, and this is 360. So Y will be its maximum lies here. Then Y will be, let us say, it's starting from here, and this will be your Vy. So it gets its maximum value at 120-degree. Okay, so 120-degree phase lag will be there. After that, Vb at an angle of -240 means with respect to Vr. So after 240-degree, from this point to 240 degrees, let us say this. So Vb will have its maximum value like this. That is Vb. So likewise, you can draw Vr, Vy, and Vb at the same diagram. Okay, so this is called as a three-phase waveforms, and Vr, Vb, Vy, and Vb are the phase values of voltages. Okay, and next, what is the phase sequence? Phase sequence, it is the sequence in which the three-phase voltages or currents are labeled. Three-phase voltages or currents. It can be voltage or current. Okay, means VR, Vy, and Vb. That is the sequence. First R will come, after that Y, then V will come in a positive phase sequence. But in case of negative phase sequence, R, then V, then Y will come. Okay, as a phase sequence, the standard phase sequence is ABC or RYB, where the phase A is taken as reference and the phases B and C will lag A by 120 and 240 degrees respectively. The reverse phase sequence is CBA. Positive phase sequence is A, B, C, again A, B, C. So CAB is also a positive phase sequence, but in case of negative phase sequence, CBA. Okay. So ACB will also be a negative phase sequence. That is the thing. Now, in a three-phase system, the order in which the voltages attain their maximum value is called the phase sequence. Means I told you that first R is getting its maximum value, after that Y phase voltage is getting its maximum value, and after that B phase voltage is getting its maximum value, and that's why its sequence is R, Y, and B, and hence it is a positive phase sequence. Okay, that is the logic. Now, taking an example, if the phases of any coil are named as RYB, then the positive phase sequence will be RYB or YBR or BRY. RYB, again write RYB or RYB. So YBR will also be a positive phase sequence. Likewise, you can get the sequence for negative phase sequence also. Okay. Then what is a balanced system? A three phase is balanced if the magnitudes of the three line voltages are equal. I already told you about this. Means there will be phase voltages VR, VY or VB, or VRY, VYB, and VBR will be the line voltages. Okay, these are the phase voltages. So their magnitudes should be same in case of a balanced system. Magnitudes should be same of the phase voltages. Also, the magnitudes of line voltages should also be same. These are the line voltages. And how to calculate the line voltages? Let us say VRY equals to VR minus VY. That is the thing. How to calculate VYB? That is VY minus VB. Okay. So V phase at an angle of minus 120. That is your VY. Minus what is VB? V phase at an angle of minus 240. Okay, so this is how you can calculate VYB voltage. So these mod values are equal to V phase, and this is the V phase. Okay, as you know that we can connect the three coils either in star connection or in delta connection. So first of all, let us see how to make a star connection. Okay, so let us consider VR, VY and VB represent the three phase voltages. How these are called as phase voltages? Because this coil is related to R phase, this coil is related to Y phase, and this coil is related to B phase. And that's why the phase voltage across these coil is VR, the phase voltage across this coil is VY, and the phase voltage across this coil is VB. That's why these are called as phase voltages. However, these terminals are related to line. Okay, so this is your R terminal, this is Y terminal, and this is B terminal. Okay, so the terminal voltages will be VRY, VYB, VRY, VYB between Y and B, and VBR. These three are line voltages because these lines are there, means these wires are called as line wires. Okay, but these coils are called as phase conductors or phases. That's why VR, VY and VB are called as phase voltages, whereas this VRY, VBR and VYB are called as line voltages. Okay, so that is the thing. Then what is the condition? For a balanced system, the condition, first condition is magnitude of phase voltages should be equals to mod of B phase. Okay, means their value should be same. And how to calculate the line voltage? For example, let us take VRY. So VRY is the line voltage between the terminals R and Y. So how to calculate that? That is VR minus VY. And what is VR? VR is V phase at an angle of 0 minus what is VY? V phase at an angle of minus 120 degrees. So this is how you can calculate VRY. That is the line voltage between the terminals R and Y, or between the phases R and Y. Okay. Then how to calculate this magnitude of the VRY? By using the parallelogram law, that is under root VR square plus VY square plus 2 VR VY cos 60, and that will be your VR square is V phase square plus VY square equals to V phase square plus 2 V phase square, because VR is V phase and VY is V phase, and cos 60. So you will get root 3 times of V phase. That is the magnitude of the line voltage. Line voltage will be VRY, VYB and VBY. These three voltages will have their phase angles also, but they have same magnitude, and that will be mod of VL, and that is equals to under root 3 V phase. So this is how you can calculate the line or phase voltage. Next, therefore, in a star connection, you please remember this. In a star connection, VL will be root 3 times of V phase. Okay. But you can observe that when you apply the KCL at this point, so IR plus IY plus IB will be equals to 0. Means 0 means this is the neutral connection. So this that is grounded. So IR, IY and IB will have their instantaneous values, and if we add these three, then their summation will be equals to 0 in a case of balanced system. And the condition is that their RMS value or the phase value should be equal. Okay, as per the above statement, line current equals to phase current. How? Because this is the phase. If IR is flowing through this phase, so the same IR is flowing through the lines also, and that's why in a star connection, I line equals to I phase. Okay, that is the thing. And in a balanced star connection, yeah, the vector sum of the line currents will be equals to 0, because IR will have I phase at an angle of 0 plus IY will be I phase at an angle of 120 minus 120 plus what is the IB? I phase at an angle of minus 240. So these are the phasor values, okay, and that will be equals to 0. Their sum will be equals to 0. In is the neutral current. If the system is balanced now, then in will be 0 only, means there will be no flow of current through the neutral path. Then how to calculate the RMS power in a three-phase system? This will be multiplied by 3. This term is related to single phase power, and that because there are three phases, and that's why you have to multiply by 3. Power, average power or RMS power will be 3 V phase. If you are considering phase current and voltage, then this will be this. Otherwise, you can write like this also, under root 3 VL IL cos phi for average power calculation. These two are the formula to calculate RMS or average power in three-phase circuit. Have you understood? Yeah, please reply. So, in star connection, these three are the voltage equations. I already told you about this, but you please remember that in any configuration, star or delta, these are the three different power values. The real power P will be root 3 VLIL cos pi, or 3 times of V phase I phase cos pi. This is the useful power, okay? We are interested in this power, only useful power and reactive power. So this is the means this is of no use, okay? But this has significant value, or there will be significance of reactive power in case of AC circuits, and you can calculate using these two equations, and the total power will be S is the apparent power or total power, that will be P plus jq. Q is the reactive power and P is the active power, or you can calculate it like this: 3 V phase I phase or root 3 VLIL. Okay, so directly you can calculate the apparent power, that is the total power in your AC circuit. That is the formula. Now coming to the delta connection. Okay. Hmm. In delta connection, obviously there will be line currents, line voltages, phase current and phase voltages. So first of all, let us differentiate phase and line. So here these three coils are phase coils, okay, or three phases. This terminal is related to R, this terminal is Y, and this terminal is B. Okay, so these three are the line conductors, and these three are phases, three different phases. Understood? So how to get the phase voltages? Yeah, plus minus, this is VR, plus minus, that will be your VB, and plus minus, so that will be your what, VY. VB, VR, VB and VC will be phase voltages, and VRY, VBY and VCY will be line voltage. For example, let us take R terminal and Y terminal. Okay, so this is your R and this is your Y node. So VR, this is the VR, and as you can see that these two terminals are directly connected, means there is no element connected between these two terminals. So obviously you can see that VRY equals to VR only, means the magnitude of VRY should be equals to magnitude of VR, means phase voltage equals to line voltage in case of delta connection. But the line current and phase current will be different, because if you apply the KCL here at this node, let us say this is the R node. So at node R, the KCL equation will be IBR, sum of the incoming current equals to sum of the outgoing currents. IBR will be equals to IR plus IRY. So IR, that is your line current, equals to IBR minus IRY. IBR and IRY are the phase currents of phases B. These are the phase currents, because BR current is flowing through this phase only and IRY current is flowing through this phase only. So line current equals to IBR minus IRY. Likewise, you can calculate for IY and IB also. So in case of delta connection, phase voltage and line voltage will be same, but the line current and line current and phase currents will be different. So how to calculate the magnitude of line current by using this same formula? So here you can write it like this: under root I phase square plus I phase square plus 2 times of I phase square cos 60, so that you will be able to get the magnitude of line current. It can be IR or IY or IB, in case, because in case of a balanced system, the magnitude of these three currents will be same. Okay, yeah, line current, and the line current is equals to root 3 times of I phase current in case of a delta connection. And how to calculate IR, I already told you this. You can get these equations by applying KCL at nodes R, Y, and B. And in case of a delta connection, there will be no neutral point. Okay, yeah, and the phase voltage and the line voltage will be same in case of a delta connection, and this P average or RMS power will be same in both the cases, means in star or in delta. That will be 3 V phase I phase cos phi, or P will be root 3 VL IL cos phi. Cos phi is the power factor of the given circuit. Uh, yeah, these three are the voltage equations that are induced in three different phases of delta connection: E1, E2, E3. Let us say, okay, and the three powers can be written by using these three equations. Okay, and yeah, this is the phasor representation. Let us say even is at the angle of 0, then there will be E2 and there will be E3, and these three are displaced by 120 degree angles, phase angles. So this is the phasor representation of three phase voltages. You can represent currents also, but that will become complicated for you, so I'm not telling this to you. These things are sufficient. Okay. Oh, hey Vamsi, are you able to understand the three phase circuits? And Sudhakar, you please tell me, are you able to follow? After that, I'll start solving the questions. Means 2 or 3 examples will be there, so we will solve these 3 questions. Please reply. The three-phase circuit will be useful when you are going to study AC generator or motor. So that's why I'm giving you brief introduction of three-phase circuits. This is somewhat complicated, and yeah, there will be simple questions related to three-phase circuits. 9:40, just 10 minutes will be there. Okay, I think you are able to follow. So let me just solve two example questions. This is the first example in which what they are asking, a balanced three-phase delta connected load is supplied. A balanced three-phase delta connected load. So I'm drawing a three-phase delta connected load. These are the loads. Okay, Z1, Z2, and Z3, and these are supplied by a balanced three-phase 400-volt supply. This is the configuration, circuit configuration. Okay, 400-volt supply is already given. That is 400 is as in case of delta connected load, line voltage will be equals to phase voltage, and that will be your 400 volt, and that is the RMS value. Okay, then what they have given, the phase current I phase is what, the magnitude of I phase is 10 ampere, 10 ampere at power factor cos phi equals to 0.8 lag, means the load is of inductive type, means R plus jx form will be there. Okay, so the total reactive power absorbed by the load is, reactive power will be absorbed by the reactive elements, and reactive elements will be L or C. So in this case, as it is of lagging nature, and that's why inductive part will be there. So how to calculate the reactive power? That will be 3 V phase I phase sine phi. Okay. So from this equation you can get the value of phi as cos inverse 0.8. After that you can put the value of sine phi here. Okay, and V phase is 400 volts, and how to calculate the I phase? I phase is already given 10. So this is how you can calculate the reactive power, and the unit will be kVAR, kilovolt ampere reactive, and that is the unit of reactive power. This is the answer. Okay, next question is, three loads each of resistance 30 ohm are connected in star. This is the star connection, R1, R2, and R3 to a 415 volts three phase supply. Okay, so 415 volts three phase supply means 415 volts is the line voltage. Yeah, if it is R phase, Y phase, and B phase. So VRY is the line voltage, and VR is the phase voltage. Okay, so they have given, always they will give the line voltage value, and its value is 415 volts already given. Then what they are asking, determine the system phase voltage. As you know that VL equals to root 3 times of V phase, then how to calculate V phase? V phase equals to 415 divided by root 3, and that will be your phase voltage. The second thing is that phase current. Phase current will be what? V phase divided by R of each phase, R1. So that will be what, 415 divided by root 3, that is your 240 volts, divided by what is the value of R, that is 30. This will come 8 amperes. I phase will be 8 amperes. Next, what we have to calculate, the line current. In case of a star connection, you already know that the value of IL will be equals to value of the phase current, and that will be 8 amperes only. So this is the simple question. Okay, then in the third example, what they are asking, calculate the active and reactive components in each phase of star connected 10,000 volts three phase alternator. Alternator means AC generator. Okay, that is supplying 5,000 kilowatt at alternator. This is the AC generator that supplies what, 5,000 kilowatt of power at cos phi of 0.8 power factor. Okay, um, if the total current remains the same when the load power factor is raised to 0.5, then find the new output. The power equals to root 3 VL IL cos phi. They have already given the value of cos phi. Then what is that? Yeah, P is already given, 5,000 into 10 power 3 equal to root 3. And what is the VL? VL is 10,000 volts. Okay, cos phi is how much? 0.8. And IL, so here you can calculate the value of IL as 361 amperes, and this is connected in star. So I phase will also be the same, 361 ampere only. Then how to calculate the active component and reactive component in each phase of star connected. Yeah, let us take R phase. Okay, so active component will be associated with cos phi, and reactive component will be associated with the sin phi. So IL cos phi is your active component. IL is 361 into zero point 0.8, this much ampere. It is asking about the current only, and this is related to the reactive component, 361 into zero point 0.6, and that is 216.6 amperes. Okay, then if the cos phi is raised from zero point 0.8 to zero point 0.9, means now it has become 0.9, then what will be the new output power? The new output power will be what? Root 3 VL IL cos phi. Okay, so root 3, what? How much is the VL? 10,000. IL is what? 361 into zero point 0.9. So this is 5625 kilowatt. That is the answer. Means when the cos phi is increased, then obviously power output will also be increased. So we want to have more power factor, and power factor will vary from 0 to 1. This is the best condition, and this is the worst condition. So this is the desirable, means cos phi that is almost equal to 1. That is the desirable condition in AC circuits. That is the thing. So the lecture is over as of now. So if you have any question, then you can ask. Otherwise, I will end the session.
To watch the complete video, download Mining Gyan 2.0 app from the Play Store and enjoy seamless learning with Mining Gyan 2.0.